Good morning, gentlemen. Today is Thursday, May the 21st, and today we are going to continue our discussion of geometric optics. All right. Remember from yesterday's lesson, we were talking about curved mirrors and the relationship between the positioning of the object itself and the location of the image where it is. And what we're going to do today is continue that discussion, but this time we're going to apply some arithmetic to it. And so we're going to work on first the formulas for curved mirrors, and then do a couple of examples of how we might look at these things and stress the location and even the size, the relative sizes of the objects. Okay, but this time we're going to apply some math. So first things first, when we talk about the formulas for curved mirrors, right, you have to understand that this is an almost 400-year-old relationship that was first delineated by Joe Newton. All right, Newton, remember, is not just famous for his laws of motion, but also for a book he wrote called Optics, which dealt really with the relationships between images and lens that are produced by mirrors and lenses. Now, the first formula is an important one. This is the relationship for a curved mirror of the focal point, the relative position of the focal point, which remember is half of the radius of the sphere that the curved mirror would be cut out of. Okay, and so we know that the focal point is going to be a number that is positive for concave mirrors because it's located outside or inside the sphere of the mirror, and we'll call it a negative number for a convex lens, or mirror. Okay. Now, the other two numbers that are associated here are DO and DI. And in this case, the D represents distances. All right. DO is defined as the distance of the object. And so it is always positive because it's always going to be located outside of the mirror. All right, just like the focal point. The focal point is outside the mirror for concave lenses and inside the mirror for convex. I said lenses again. I meant mirrors. But so essentially, if the thing is outside the mirror, it's positive. If it's inside the mirror, it's negative. So DO is always going to be positive because the object can't be located inside the mirror. All right, so this number, DO, is always going to be a positive number. Now, DI, on the other hand, is the distance that the image is. All right, and these distances, by the way, are from the vertex of the mirror, where the principal axis actually strikes the surface of the mirror. And DI is going to be positive for a real image, an image that can be projected, one that's found outside the mirror itself, but negative for a virtual image, an image that's found only inside the mirror. Okay. Now, the formula itself, 1 over F equals 1 over DO plus 1 over DI, is not, I repeat, not found on your handy-dandy reference tables. And so for your homework purposes and anything else, you might want to go to the section on waves and write in this formula. 1 over F equals 1 over DO plus 1 over DI. Now, that's not the only relationship. That's the one that we use for distances. But there's another relationship that's important as well. And this deals with the relative sizes of the images, all right, along with the relationship of their distances. Remember that for certain objects or certain distances, the image will appear to be larger than the object. And for others, it'll appear to be smaller than the object. And this relationship is one that is a proportional relationship. The size of the object is abbreviated as SO. The size of the image is abbreviated as SI. And of course, DO and DI refer to the distance of the object and image from the vertex, respectively. Now, this is, again, a proportional relationship. The size of the object over the size of the image is equal to the distance of the object from the vertex divided by the distance of the image from the vertex. And again, this formula is not found on your handy-dandy reference tables. And so if I was you, I'd get those reference tables out right now and write it down in the waves section of your tables. Okay, just so that you have it for use on your homework assignments and any review assignments that I might have in the future. Okay, so how do we put this all to work for us? All right, well, it is a relatively straightforward kind of or set of relationships here. So for example, number one, for example, what we're going to do is start out with a set of relationships, and we'll start with a 5 centimeter object, all right? And so that's going to represent our value of SO, and so that's going to be 5.00 centimeters. But notice that it's given in centimeters. So I'm immediately going to convert that to 0.050 meters, okay? It's placed 0.80 meters from a concave mirror. So DO, this is going to be my distance for the object, is going to be 0.80 meters from a concave mirror whose focal length is 0.20 meters. Now, based on what you remember from the lesson the other day, an object placed 0.80 meters from a concave mirror is more than twice the value of C, all right? If F is 0.20, then C is 0.40. And so in this case, we got a concave mirror. Here's our principal axis. If this is F and this is C, then my object is placed somewhere about here, okay? Now, I'm asked to describe the image. Now, if you remember from our description the other day, the image is going to be, all right, this is going to bounce off of the focal point. Whoops. And then I'm going to send another ray of light literally right through the focal point, and it's going to reflect parallel to the principal axis. And I've really kind of messed this up, but the image is going to be located somewhere in here. All right, and so the image should be between C and F. So when we do our work, we should be able to figure out that from there. And in addition, the size of the object should be smaller than, the size of the image should be smaller than the object. So we can use that to check ourselves. So that's the first thing that we need to do. The image is real. All right, so we're describing the image. The image is real, it is inverted, and it is smaller than the object, okay? So the first thing that we're going to do is try to determine its position. So we know that the formula here is going to be 1 over F equals 1 over DO plus 1 over DI. That means that 1 over DI is going to equal 1 over F minus 1 over DO. All right. In this case, I'm just going to do a quick plugging and chugging because I know you guys hate fractions. So 1 over 0.2, all right, minus 1 over 0.8, All right. And if we look at this mathematically, 1 divided by 0.2 minus 1, 1 divided by 0.8. And that's going to give me a value of 3.75. So, but that's 1 over di. If I take 1 divided by 3.75, that's going to give me 0.27. All right. So di, the distance of the image, is going to be 0.27 meters. All right. Now, does that make sense? Well, we said that the image is going to be located between C and F. Well, if F is 0.2 meters from the vertex, then 0.27 meters certainly does make sense. So that's a good answer here. Now, in order to determine its size, I know that the relationship here is SO over SI equals DO over DI. The math here is a little bit easier in that the size of the image is going to be equal to SO DI over DO. All right. So that's going to give me, let's see, SO is 0.05. DI we just calculated as 0.27 and divide that by the DO value, which is 0.8, and that's going to give me an SI value, a size of the image of, let's see, 0.05 times 0.27. Now that's a rounded number, but we'll accept it for now, over 0.8, and that's going to give me an image of 0.017. Or 1.7 centimeters. Does that make sense? Well, the original object was 5 centimeters in height. The image of that object is 1.7 centimeters in height. So it's smaller than the original object. And so yes, indeed, it does make sense. All right? Okay, so that's example number 1. Let's move on to a second example, shall we? Same kind of setup here. I'm going to give you some information and ask you to use the two formulas in order to calculate the value of our of a couple of other things. So I've got a 3.0 centimeter object. All right. So the size of the object SO is going to equal, and I'm immediately going to convert that to 0.030 meters. It's placed 0.50 meters from a converging mirror. That's a concave mirror. And so the distance of the object is going to be 0.50 or half a meter, whose focal length, F, is going to equal 0.10 meters. Okay. Describe the image, determine its position. All right. So again, here's my my mirror. Here's going to be the principal axis. I'll put the center of curvature about here, and therefore the focal point about here. Now, if the focal point is 0.1, then the center of curvature is going to be 0.2. In this case, then the 0.5 meter object is going to be located somewhere way out here. Okay, and again, I'm going to send. I'm going to send an ray parallel to the principal axis. It's going to reflect through the focal point. I'm going to send another one through the focal point, which is going to be reflected parallel, and that's going to give me an image which is going to be located again right about here. So again, somewhere between the values of C and F. So so we describe the image. It's going to be real, smaller than the object, and inverted, and located somewhere between C and F. So again, 1 over F equals 1 over DO plus 1 over DI. If I want to find the location of the image, I'm going to have 1 over DI is going to equal 1 over the focal length minus 1 over the DO value. That's going to be then 1 over 0.1. All right, so 1 over 10, that's going to be 10, minus 1 over DO, that's going to be 1 over 0.5, which is 2. So 10 minus 2 is going to give me a value of 1 over DI equals 0.8. Okay, because 1 over a tenth is 10, 1 over a half is 2. 10 minus 2 is, nope, I lied, that's not true. It's going to be, let's do the fractions. So 1 divided by 0.1 minus 1 divided by 0.5, and that's going to give me 8. All right, and then 1 divided by 8, where is that button? There we go, is going to be 0.125. All right, so 1 over point all right, so so DI is going to equal 0.125 or 12.5 centimeters or 0.125 meters. Now, does that make sense? Sure, because the focal length is 0.1 meters. All right, and so we expect that the image to be located a little bit further out than the focal point, right, based on our diagram. And so 0.125 meters makes perfect sense. To determine its size, the size of the object over the size of the image is going to equal the same ratio of distance of the object over the distance of the image. And so therefore, the size of the image is going to equal the size of the object times the distance of the image divided by the distance of the object. And so the size of the image is going to equal, the object was 0.03 meters. The distance of the image we just calculated is 0.125 meters. And divided by, and actually we'd have to change this to 0.13 for sig fig's sake. And the distance of the object is going to be 0.5. And so that gives me the size of the image. And remember, the size of the image based on our diagram should be smaller than the size of the object. And so in this case, 0.03 times 0.125 divided by 0.5, and that gives me 0.007 0.75 or 3/4 of a centimeter. All right, so 0.0075. Now, is that smaller than the 3 centimeter object? You bet your sweet bippy it is. And therefore, this all does make sense. All right. The only thing I should have fixed was this should be down here should be 0.13 because all our numbers rather only have one significant figure. Okay, so it's time for you to do a little practice on your own with this. I'm going to upload a homework problem sheet for you, and your homework for this evening is to do questions 1 and 2 on the homework sheet. All right. Let's see. This will be due on Tuesday evening by the end of the day. All right. Have yourselves a wonderful Memorial Day weekend, and I will see you after the holiday.